Good afternoon, everybody. Thank you for coming. I am Luiz Villa, and I'm going to present to you unlocking software-defined power electronics with Zephyr in this BoF session. Thank you very much for being here. How many of you has ever dealt with power electronics? All right, a few hands. That's good. How many of you had to deal with power engineers? Okay, same hands. All right. You have to deal with them. Yeah. So we are going to talk about power electronics, and power electronics is not an easy topic. So I'll try to, cope with me a little bit. Give me some rope. I'll try to make this as easy as possible. Hope it works. I am an associate professor at the University of Toulouse. Unfortunately, I could not be joined by my colleague Jean, who is the hardware engineer and a co-supervisor organizer of the OwnTech project that we're running right now. We work at the LAAS-CNRS laboratory. I work at the university, but the French system, we are half in university, half in the lab. So half of my time I spend doing research on the lab, and it's the biggest laboratory of the National Research Council in France. We have 300 plus people, and we go from robotics to power electronics, which is what I do. We are heading the OwnTech project, whose objective is to create a low-cost, versatile, reprogrammable, open-source power electronics technology. Don't hesitate to go to our website, owntech.org, for more information. If you want to know more about the project, at the end of the presentation, I got some extra slides. I can also talk a little bit more about it. So the way I'm going to do this is I'm going to talk about power electronics, what it is, and then go into what is software-defined power electronics and our study case, and finish with the lessons learned from our endeavor using Zephyr here. As you may all be aware, there's a great energy transition taking place in developed and developing nations. And it has a lot to do with the emergence of cheap renewables, batteries, but also of the sort of a making philosophy where people are having more and more access to technology that they can try to hack and create stuff with and learn with. What's underpinning this great energy transition is power electronics. So what is power electronics? Power electronics is a branch of electrical engineering. It's electronics that is made to handle power flows. It can go from milliwatts to megawatts. And you hear a lot about DC to DC or DC to AC. So these are what we call power conversion types. We can do single phase or three phase. Usually that's the kind of stuff you're going to find in the market. There is a historical bias in power electronics, is that it's very function oriented. When we talk about power electronics, you never hear about power electronics. You hear about battery charging or energy management or motor control or grid connection, but you don't hear about power electronics per se. And this sort of bias is what drives a lot of the way power engineers think about their profession and the way they do power electronics themselves. How does it work? Now, I've tried to run through this without being too much electrical engineering, but the thing is, power converters, they regulate voltage or current in an output, right? To do that, they use a control loop. And the control loop measures something, goes through the control loop, and gets something out, in and out. The power flow that is being dealt with here is controlled via PWM signals. PWM signals are square wave signals with a certain width that can move over time. Fixed frequency, just the width of the wave is moving. And this width is called a duty cycle, and that's what usually PWM power converters use to control the flow of power. That means that you have in the input you have a flat line which is of DC voltage, for instance. It's going to get chopped, and then it's going to get filtered into these nice triangular waves, which ripple around an average value. And that's it. That's power electronics for you folks. It's what we try to achieve when you're running a power converter. So real time is very critical here. The switching frequency period, the period between switching frequencies is the time that you have to pull off whatever calculation you think you had to do. So we are very time critical. And because this is very time critical, power electronic engineers tend to throw digital stuff out of the window and do everything analog, or at least try to analog as much as they can before they reach the digital realm. And we believe that the time is ripe for a digital power electronics. That's what we are betting into. So why? Well, why bother digitalizing power electronics? Well, decarbonizing the economy will require more electricity, and more electricity will require more power electronics. So digitalization has emerged in the past as a means to reduce time to market and standardize development of solutions. This has already been done. So there are benefits of doing this, and energy transition will greatly be accelerated if more people can use modular, standardized, and digital power electronics. The place where we are is an example of it. We moved away from those type of computers into our type of computers because we started to standardize, miniaturize, digitalize. So that effort can also be done in power electronics. At least we believe so. We have examples of digitalization that most of you already know with Arduino, Raspberry Pi, microbit. And this is a nice example from Siemens. They did a small software-defined inverter in 2018, what was called the Tapas board back then. So what's the state of the art? How is digitalization taking place? What's happening right now? Well, let's take two examples to understand digitalization. We have IoT, which basically means we create this nice, fully integrated stack, and we do no more bare metal, and we have our target in our nice board condition for us to plug and play. So that's one way of digitalizing stuff. Another digitalization that's taking place, if you look into power electronics, is digital power controllers. They are still bare metal, but they are super flexible microcontrollers with very specialized peripherals. They have high integration between these peripherals. They have specialized real-time control peripherals, and they have integrated fault management and telemetry protocols. So this stuff is made for power electronics. So the problem here is on which target can we combine the abstraction API approach of IoT with the performance of dedicated analog peripherals? How can we do that? With what can we do that? There are a few examples of digital power controllers. Some of them are function-defined, which means that they are multi-phase converters. For instance, multi-phase converters for CPU power delivery, they provide telemetry, they optimize control laws, but they are tied to specific case, DC to DC conversion at a certain voltage level. And there are reprogrammable SOCs that we can use, which have the dedicated high-resolution PWM generators that can dedicated fast analog peripherals, ADCs, DACs, and comparators. They have dedicated hardware for fast control computation, but some of them require vendor-specific language or libraries. They are very, very niche, very hard to get into. So if we summarize, when it comes to digital power electronics, there is a stack, a de facto stack, that we have to think about. On the top of the stack, we find the software, which runs on the MCU, which has a communication task and a control task. And this is something that we can see as being IoT-ish, kind of. And then we have the hardware, which would be the peripherals that have the timer-based PWM generators and the ADCs, and they close the loop that we saw before for the control. So this is the stack that we need to digitalize. The question is, how do we digitalize this? And what are the constraints around the stack that require us to digitalize it? And that brings us to software-defined power electronics. Now, before we talk about software-defined, I need you to take that stack a little bit further so we understand the constraints that are imposed on the microcontroller. So then we can talk about its digitalization. In the majority of cases in power electronics, we can handle the majority of conversions in power electronics with three algorithms, with three different control techniques, sorry. What it's called in the power electronics domain, it's called the voltage mode, the current mode, and the DC to AC conversion. So these are the big three which cover 90% of the use cases. So that's where the effort of digitalization should concentrate, in our opinion, because then you solve 90% of your cases. We're going to look them over, try to understand them, so we can deduce the constraints that impose on the digital SOC, and later on how we can abstract that digital SOC via digitalization. So we take the same schematics as before. This is what I showed you. And in this case, we're doing the voltage mode. And in voltage mode, we take the measurement through an ADC. It's handled by a DMA to the memory. The microcontroller will then take that, do a calculation, update the high-resolution timer, the PWM goes back, and the loop is closed. This is what I showed you before. It's not hardware intensive, as in the peripherals that you see here are not as specialized as you're going to see in the next ones. We are doing control on average measurement. That means that we are measuring, we have some time to do the measurements. We don't have to do that instantaneously. We can have a control bandwidth that can go very high or can be very low, depends on the type of application you're doing. So that's adaptable, and it can fit many budgets of SoCs. And it can be done with a non-specialized microcontroller. You can actually pull this off with something that is not meant for that, and you can have a quite decent result. But there is one catch, is that we need an average measurement. And on this triangular waveform post-filter, we cross, it's a triangular wave around that ripples around the average. So there's only one moment that you have the average value. It's exactly at half of your duty cycle. If you miss that spot, you're either measuring something that is below or above the average. So you're either underestimating or overestimating your average, so you introduce error in your control, which is a problem. So you need to be very precise in your measurement. Some SoCs do not provide you with that triggering precision of the ADC, which we're going to see later on. If we go to current mode is a more complex, more hardware intensive, where there are two loops. You have a control loop here, and you have a voltage loop. And the control loop is basically instantaneous. You have this measurement which is hardwired to a comparator, and the comparator has a threshold. And as soon as your triangle hits the threshold, it resets the IHR timer. So that's very fast. It's at the switching frequency speed. It is the setting of the threshold that is lower, that is taken by this slower control loop, right? So you see that you have the same, on this low control loop, we're basically on the same ballpark. We have the ADC, the DMA, the MCU, but then suddenly we have a DAC that is here, that is generating our threshold, goes into the comparator and goes into the HR time. So we're adding more hard, and that's for one leg. If you have several legs, because you need to parallel, you need more current, that means you're multiplying the number of peripherals that you need to synchronize and need to make them work all together. So it is necessary to have a direct connection between ADC, DAC, comparator, and an HR timer when you're running the show like this. So you start to have horizontal connection between your peripherals that do not depend on your CPU, on your MCU. And then you have the last one, which is DC to triple phase AC. I wanted to illustrate. Now, I'm not going to go through the details. What I want you to understand, like taking a step back, is that there's a lot of stuff going on inside the microcontroller. So this is very, very, very calculation intensive. A lot of microcontrollers which are dedicated for motor control, they have actual accelerators for doing trigonometric calculations so that you can go through this as fast as possible. But here, because we're running a motor, the motor is running in hundreds of hertz. You have the time because you have more bandwidth. Your microcontroller is running on the mega, your motor is running on the hundreds, so the distance is such that you can calculate yourself away. But you still should be careful because there's a lot of calculations to be done, right? And sometimes, if you want to make your life easier, you actually can add external measurements for the position of your motor. Sometimes you do sensorless, which even adds more calculation to your problem, to more of a calculation burden for your SoC. So we get to a more thorough vision of the digital power stack. We had the same stack before, but now I've added the different loops. So we have the ADC that goes through a controller accelerator, the DAC, the analog comparator back to the timer and into the power hardware, and that's the current control. And we can have the ADC going through data handling to the high-level control and back for the voltage mode. So now I added the whole shenanigans. And this means that we have fast control tasks, fast acquisition, fast communication needs, and very precise timers and PWM. So those are our needs in critical real time. We need multiple triggers, multiple DMAs, ADC and PWM synchronization, and a very dense and efficient peripheral to peripheral connection. And then we have communication needs. We have fast low-layer communication for decentralized control and synchronization. If we have several modules, they need to synchronize, they need to share current and share information. We need that communication layer. And we might have a slow, higher layer communication, which is monitoring the flow of power in different modules and dispatching power between them. So all this stuff has to be in the digitalization process. And usually, people who are doing power electronics, they're pulling this off, going from bare metal all the way up. That's why it takes so long and it's such an inaccessible technology for now. And this is our stack. This is how we got that problem when we cut it into pieces and try to put it together and try to solve it. Before I go in, any questions? Yes?
Yeah, one question I had was, I thought another motivation to push things more into analog or like fixed gates rather than software is that it makes it a lot easier to pass the safety certification. Like, I thought that was another thing that pushed you away from trying to do it in software because then you have it's a much tougher thing to certify.
Indeed. So the question is, the certification is also a reason why we would run the show all in analog. That's true. Some digital power sockets, they actually integrate. You can hardwire your measurements to some of the leads and code that into your microcontroller so that it is a hardware check. And if the check goes beyond a certain threshold, it cuts the power. So that kind of stuff is integrated in new digital socks. It is features that we can see in digital socks emerging today, indeed. Okay. Even if you're not doing current control, if you're doing voltage control, you can still do that kind of, implement that kind of a security safety feature and it works. Yes? Sorry, say.
Where does Zephyr come into?
It's coming, it's coming. I needed to, I took the bet that I needed to give you these constraints upon which they were put upon me, so then I can explain to you how Zephyr is going to solve all my problems. But it's coming. Zephyr comes when I go to this, when I get to our stack. We have a stack that goes from the power hardware, the hardware MCU, the fast control task, the slow control task, and the communication. And you can kind of see that Zephyr is going to start appearing as soon as I get out of my power hardware, and I need to configure this stuff. Zephyr is going to help me. When I need to create my fast control task, Zephyr is going to help me again. When I need to create my slow control task, Zephyr is going to be there, and so on and so forth. And you're going to see that Zephyr shows up quite early in the stack, and it follows me all the way to the end. This slide is more thorough if you can download it and read it later. I just want to go through each one of the blocks, block by block. Now, the power hardware. We wanted to make a reconfigurable, reprogrammable power hardware, right? We want people to use this and create a community around it and build solutions from it. So we wanted something to be reprogrammable and be stackable so we can put them in parallel and raise and reach higher power. So how do we do this? How do we go about creating such a power converter? So if you take electric power, it's current times voltage or voltage times current. So if you trace current in your y-axis and voltage in your x-axis, and you plot a constant power curve, an ISO power curve, you notice that on the left-hand side, you have a low voltage, high current section, and on the right-hand side, you have a high voltage, low current section. So basically, if you're doing DC, you're on this side. If you're doing battery, if you're doing DC motors, you're running the show here. And if you're doing AC or if you're doing higher voltage, you're going to be on this side. So you have to cut that stuff in half because my power converters are made of power switches, and power switches are designed to operate in different spots in this curve. So you have to find a place where you cut this and you decide where you want to operate on the low voltage and where you want to operate on the high voltage. We decided to cut at 100 volts, and we designed a board that can operate below 110, 120 volts, 110, and someday, and learn all we can with it so we can design the board that's going to operate on the high voltage side as well. And this is our board. If you want to know more about the schematics and how it works, I have some extra slides. We can do that in the questions as well. But this is the view of the power board. It has it is a 300-watt board with 2 channels on the low side. So you have the VLOW 1 and VLOW 2 here, and 1 channel on the high side. So there's one side who has a higher voltage than the other. 8 amps per channel, 16 amps in parallel. They can be put in parallel. On the low side, we can be between 12 to 72 volts, and on the high side, we can go from 40 to 110. We can go to 24. We can go a little bit lower. It still works. We can run a DC to DC buck or boost. That means that we can input on the high side and output on the low, or we can input on the low or output on high. It goes both ways. And we can also do DC AC single phase with using both channels at the same time. Because we want something that's reprogrammable, we need to have full observability. So we have voltage measurements for both low side channels and the high side channel, and current measurements for all channels as well, plus a temperature sensor. Which makes our power converter de facto a data logger, and this is important because I'm going to get back to it. There's a data aspect to, open data aspect to our project as well. Here is a table that summarizes the main functions, power functions it can provide. You can take a look at it later as well. What I wanted to show you is a little bit Arduino-esque setup, where one example is you have input with a PV panel, and the output is your battery. So you're charging a battery with the board, as an example. You can also have 2 batteries connected together, so they are charging each other and they are helping each other. You can use it to drive a DC motor, or you can use it to 3 of them stacked together to drive a 3-phase AC motor on low voltage, but still it can be done. And we have the different conversion functions and the type of use case that I put on the table here. So now that we have the power hardware and we know it can provide us the functions that we need, it comes the part where we go into the digital hardware. And we try to, and that's where Zephyr is going to start to come into place. Before talking about Zephyr, how do you go about, what are the criteria of choosing your digital hardware? And this is important. You have 2 big constraints when you're doing, when you're controlling a power converter. The maximum bandwidth of a converter, it's 1/10 of its switching frequency. That means that you have your switching frequency, and 1/10 of that is how fast your converter can create a sine wave for you. So say you're switching at 1 megahertz, the fastest, reasonable sine wave that you can do is 100 kilohertz. I know usually it's half, but we're doing the engineering side where we get some extra leeway here. So you have, that's the maximum bandwidth of your converter. So if you have a converter, usually you don't have to go as high when you're using, say, a motor driver or something like that. These are very low speed, low frequency. But if you're using your converter to emulate the behavior of something else, and you need to have the transient response and you need to go fast, then those are the restrictions you're going to be confronted with. At the same time, you have your application bandwidth. And your control has to be at least 10 times faster than your application, because otherwise you can't really control it correctly. So those are the limits you are going to be confronted with. The voltage mode operates quite well in between the control frequency, the maximum converter bandwidth. And the current mode, which requires hardware acceleration, usually is the way we do to push this all the way to the switching frequencies, like I showed it to you. The current loop is going to be operating at the bandwidth, almost at the switching frequency bandwidth. So that means that it can catch any very fast transient that the voltage mode is going to have a hard time doing. Or if you want to do that in voltage mode, you need to have a hardware accelerated voltage mode, which is much faster. It will also constrain your sensors. It means that your sensor, your voltage sensor, needs to be at least 10 times faster than your application. And your current sensor needs to be at least 10 times faster than your switching frequency. Otherwise, you can't catch it. You can't catch the transient. And as you add legs to this, everything becomes more complicated because it compounds the needs of your power converter. And finally, the switch technology that you choose is going to be linked with the choice of a microcontroller. If you're pushing for switch technology that goes very fast, you're going to be hard pressed to digitally define it with a normal microcontroller. You're going to have to go for FPGAs or something more fancy. And in terms of digital hardware, like you've seen, it's important to have reprogrammable ADC peripherals, ADC modes of operation that they depend on your control mode. For instance, here I'm in voltage mode. I'm using one ADC to measure 2 voltages, using the DMA to fill up a buffer that is then queried, it's looked on by the MCU to do doing its calculations for voltage control. And if I'm doing current control, I have the ADC one going through the DMA into an FMAC that accelerates and gives the results straight into the HR time, so I don't have to go through the MCU anymore. So there is a need to accelerate calculations in many applications, and there is a need for the interconnection matrix. We need to be able to connect peripheral to peripheral. And this is something that Zephyr, we had a hard time to do using Zephyr. There's also a multi-mode data acquisition. Sometimes you're going to have a situation where you need to measure a voltage and a current at the same time, very precisely, very close to each other, so you can calculate power. And you can link them together with 2 separate ADCs, for instance. In other cases, you want to have one very fast measurement of the voltage and slower measurements of you can cycle through all the other measurements because you're just doing telemetry of it. So you have to have this flexibility of attaching different voltage measurements to different ADCs and having different strategies of measuring your power converter. So we get to the microcontroller we chose. We chose the STM32G4 because it has a very good HR timer with a very high resolution. We are switching at 200 kilohertz. We have 13,000 points of resolution, which is fine. It means we can control voltages and currents at the milliamps or millivolts level. We have 2 ADCs with reassignable ADC channels, 2 DMAs, an FMAC, a CORDIC for trigonometric functions, and the FPU. And it comes Zephyr, right? So what we wanted to do is to be able to abstract this. So we needed an RTOS, because the RTOS have all the benefits you guys all know about having stacked and natively implement abstraction, out-of-the-box IoT, driver-oriented programming, and low-level APIs. So we created some of the low-level APIs. We had to do a hardware configuration API and a data acquisition API so that people would abstract the use of Zephyr. Our inspiration for software obviously was Linux. Have a lightweight code like they do in FreeRTOS, or have very simple to use IDE like they do in Arduino. And for some folk have actually almost like a no-code craze where they're looking at blocks and they're connecting them together, which usually happens when control engineers are dealing with power electronics. So we chose Zephyr for all the obvious reasons, and that's why I'm here. And the way we use Zephyr is that one of the things that was very hard for us before we got into Zephyr is the ergonomics. So we built up our user chain, let's say, our ergonomics of Zephyr, that we have an outer VS Code envelope. We use platform I/O so that people don't have to use the command line. They don't need to know how to use West. They can just use platform I/O and press a button. We host our libraries on GitLab, and platform I/O will automatically, whenever you tell it to, it will download them and make them available for you, so then you can use them on your code. And it also automatically handles third-party software. So we use some code for communication, which comes from someone else. And we just, when platform I/O compiles, it will automatically pull that code and put into it Zephyr and then compile it. We wrote the low-level APIs so we can abstract the driver, so people don't have to do the driver declaration of Zephyr. They can call a function, I want, hardware config, initialize, buck converter mode, or hardware config, update, buck converter, duty cycle, and then the value of the duty cycle. And so we wrote our HR timer because there was none in the Zephyr, and we rewrote the ADC driver because we needed to have this very precise trigger coming from the HR timer to the ADC, so the ADC would measure exactly at the moment we wanted, which is the average value control. And we had to tweak the timer as well a little bit because measuring the position of a motor is done by using timers. So we had to tweak the timer so it can be used as an encoder. And we also had to tweak a timer so we could synchronize and trigger the control loop. And how did we do this? Well, we have one way of using it is using the main. So we have an Arduino-like approach where basically you have a main.cpp where the user can declare the variables. They do two functions of hardware and software setup. So the hardware setup is where you say if you want buck, if you want boost, if you want to activate all the measurements, or know which measurements go in which ADC and that kind of stuff. So that's the setup. The software setup is basically I want to create this or that thread, but it made in a way so that the user does not know what they are creating a thread. And then we have the three loops: the communication, the application, and the fast control loop. The communication loop, I put the CAN there because we are using CAN, but that's where Zephyr starts to shine because you can do whatever you want. So it's a thread dedicated to communicate with the outside. For now, we have the CAN-based communication, but we also have the pinout that would allow us to go through Bluetooth, through UART, whatever. Then we have an application control loop that I just learned that we have a state machine application for Zephyr, and I was looking at it. We basically do a state machine, but we did it by hand with a switch case, and now I'm going to use the Zephyr application. And then we have the fast control loop, where we call the data acquisition so we can pull all the data from the buffers that we need. We run the control library that is available, that we made available for the user. So we declare the PID control or whatever other control we need. And then we use the hardware configuration to update the HR timer and update the system. So it's fundamentally transparent for the user. They don't even know they're using a Zephyr if they don't want to. We pushed this a little bit further because in power electronics, a lot of people don't code. So it's a very particular community because people can calculate something very precise with a resistor or with a very exotic electronic scheme, but they don't know how to code. So what we did is that we found a way to use MATLAB to auto-generate code. So we give the function calls of the abstraction layer to MATLAB, so that MATLAB can then auto-generate the code that we can then just feedback. So you have, with pressing two buttons, the auto-generate code of MATLAB and the compile and flash from Visual Studio Code. The code is into the machine and it's working, it's running. It was a very big benefit. We did this about a month ago, and we are now starting to write our MATLAB library so we can have a bunch of different modules that people can use. These ones here. And they can leverage MATLAB power. There's a latency going on here. Yeah. So last part of our stack. So we got to this point where we have the Zephyr that we abstracted. Our users can code, and our users can use MATLAB to create their control code. Now they need to export all the data of this de facto data logger can provide them, right? And again, this is where Zephyr is quite a good help. Right now we are using. Come on. All right. This worked? Yes, it worked. Okay, so what is necessary here to understand is that there's a low-level communication bus where two modules can talk to each other, and that goes very fast. So you have the highest bandwidth possible, closest to where time is critical, right? Then there is a communication middleware through which you can funnel up information all the way to your front end and then back if you need to act on your system. So we need a multi-purpose communication with data parsed in bidirectional flow, with some sort of data treatment, data aggregation, and system diagnosis as well, so we can know if the power converters are failing, if there's a problem on the bottom. And in power electronics applications like grid control, grid injection, grid forming, or some other applications, battery charging and so on, you might have different control architectures. You might have a hierarchical control architecture. You might have a decentralized, where each power converter is handling its own target. Sometimes they're sharing information between themselves. So you need the flexibility to be able to deploy different types of control architectures. And comes our digital controller integration. This is where we put our microcontroller in a board that is isolated and feeds itself, gives us the possibility of expanding more sensors, and we use an RG45 to use the CAN communication, so we can daisy chain a lot of converters together, and they all talk into the same CAN bus. Big shout to Martin Jäger, who helped us a lot in realizing that this solution was possible and actually importing it into our project. 38. Come on. I think I have a power problem. So what are the use cases of this communication hardware? You can see here, if you have two power converters doing master-slave control, so one is running the show and telling the other when to come in and help him. So they're measuring current or voltage and sharing information between themselves. You can also have integrating the measurements from the encoder, or simply sending data out through a Bluetooth device, or creating or adding the communication middleware and doing a more complex system. What we did to get to this point is that we use ThinkSet on a low level, so we can talk on the CAN bus. ThinkSet was created by the same Martin I talked about just before. You can check out his website, thinkset.io, and it's a target agnostic data parsing system. So basically, it parses the data that you declare on a folder and on a file that looks a lot like a, I wouldn't call it a device tree, but it's like sort of like data nodes and a data tree. And you can build your data structure and flash it into your power converter, so that your power converter is broadcasting the data that you tell it can broadcast, and you can create all sorts of access to that data, safety features, so on. So he's done a very good job on that. So we integrated that into our project because it's open source, and and Martin is amazing. We also started to use ESP32 because it's everywhere, it's low cost, and also because Martin also, through the LibreSolar, he came up with this dongle where there is the possibility, which is at the end of the daisy chain I was talking about before, and we are currently trying to contribute to, we looked it up, and we have an engineer who is rerouting it to make a new version of it. And then we get to this front end, and this front end does all the data aggregation for us. What we've chosen so far is to use the ThingsBoard solution, which is a turnkey solution for that, but it's also open source, so we can host the data in our servers and so on, at least for the beginning. All right, how much time do I have left? I still have some time, all right? 10, 50, okay, plenty of time. So lessons learned. The star and the circle. Power electronics have a very niche need for combining CPU flexibility and hardware acceleration, so that manufacturers have solutions, but they're still bare metal coding. And we really need, it would be very good to have this peripheral to peripheral via DMA interface and peripheral interconnection matrix as a way of connecting this stuff together. And this in Zephyr would be a great help. We had to implement it ourselves in many cases because, and also I understand it's a very niche request to have access to this interconnection matrix. So everything is possible, but not always available. That's one key takeaway from what from our experience. And then we said, well, everybody talks about device tree, right? So we're going to talk about device tree a little bit. It is necessary to create an abstraction for power electronics in hardware in Zephyr. I mean, it's necessary. We think it's necessary. And this would be a truly vendor-neutral support for power electronic systems, right? But how do we write this abstraction in Zephyr? So this is something we're starting to work on. The fragment of DTS is probably completely wrong, but the idea here is to be able to say, okay, this is the power hardware, it's compatible with this or that vendor, and this is the power leg, which can either do buck or boost, or only one of them, or both of them, or it can do a flyback. And then this is the HR timer it's attached to, this is the pin of its high switch, of its low switch, and so on and so forth, all the way to the end, so that you declare this power hardware. And when you parse that and you compile your API, you know which power hardware you have, and you can check if it's possible to do a buck or a boost if your HR timer. You can do some automatic checking to see if what you're trying to build actually is buildable. And you can also hard code limits in terms of current, in terms of voltage, and so on and so forth. So that can also always help. And we can go much further. So what is the pin for safety that needs to be connected, and so on. Another lesson that whatever that goes up should eventually come down, and that means that embedded systems need to take data and control targets. So they take the data and they act on something. So having, in Zephyr, it has a start of an uplink, which means that we have the sensor API, but it is still quite a complex endeavor to make it work. Or maybe it's just complex for us, maybe, but it's still, we found it to be a high entry ticket. And we don't have an actuator API. We don't have an API that's generic enough to say, all right, if I need to act on something, how do I describe that? And this is not necessarily an easy thing to do. We're saying that this is potentially, Zephyr would benefit a lot from it, because we could, like Jared showed us the other day, we could do the servo motor, or we could do other types of actuators with some sort of general abstraction layer. That could be an interesting thing. At least for us, it would be extremely interesting. And another lesson that we learned is that we need to break down big problems into small parts. This software-defined power electronics problem is very complex, it's very big. And we eventually got to the point where we are going to separate the brain from the muscle. That means that we are basically at the point where we had our previous version of the power converter. This is the new one, who is coming out soon, which we hopefully will design, freeze it, and start to produce it. So we have the power converter where the STM32 microchip was soldered on, and now we separated it so that we know there's a lot of people in the community of power electronics who have the my baby effect, and they have their power converter they've been working on for 10 years. It never worked, but they still want to make it work, and they still want to pursue that course. It's fine, but they need just the brain. They already have the muscles, so that's fine. They might benefit from it and from the abstraction layer that we're trying to build. And at the same time, there are some people who already have the brain. They already know how to code Texas Instruments or NXP or whatever for years now, and they don't want to change. So they just want that muscle. So decoupling them with something that we think is going to help us foster this innovation and bring this community of power electronics together. Further, if you guys want to take a look, I can pass it around. Okay. And I think that's it. So that's it for the presentation. We have time for questions, plenty of time. So go ahead, shoot away. Thank you.
How do you handle the power up sequence?
That's a great question. We have, The question is, how do you handle the power-up sequence? This is a great question. There are different ways of handling, there are different levels of handling that problem. There is the power-up itself. We have developed a small power converter that feeds the whole board. And that power converter can go from 10 volts to 110 volts in the input. So then when we power up the high side, it powers the board. So it powers the microcontroller, and the microcontroller starts. So this is on the power side. And if you feed from the low side, because of the way the topology is, there's only a diode that goes in the other way. So the power gets to the high side, so it powers up. So either way, if you're connecting your source on the low or on the high side, it powers up the board. And then you have to think about your control, indeed. That means the way we code now, we add some communication aspects to it so that it does not turn on unless you turn it on somehow. So this is something that we use, and we always recommend people, when in our tutorials, we make people build the communication task first so they can turn on and off the power converter, and then the power task, so that we are sure that when they get to the low-level power handling, if they push the button, they're not going to blow the whole thing up, at least not in the initial sequence. Maybe if they started, they're going to blow it up, but usually this is not the case, which is quite nice. The board, the circulating, is about a year old, and we tested it with about 30 people, and nobody managed to blow it up, which was quite surprising for us.
Can I put my cape to go like this?
You can, I'm pretty sure there are people who can blow it up, but so far we haven't not found it. Yes.
Question from online.
Why didn't we use FPGA technology? That's a very good question. The first thing that came to our mind, we talked about FPGA with, we have a colleague, Clément Fouché, who is also a specialist in FPGA, and he always tells us that what we're trying to do is make a microcontroller behave like an FPGA. One of the issues we had in the beginning is that we wanted to have an open source way of coding and to have a very nice ergonomics of coding. And FPGA, it does not really provide you that nice ergonomics of coding. I mean, people may disagree, but the coding with VS Code and Platform I/O and in C, it's something that is way more accessible for power electronics folk who don't really like to code in the first place than going through VHDL and some other arcane way of coding something.
It's a lot cheaper too.
It's a lot cheaper and so on. There are many. It's an ergonomics issue. I know it's. I was surprised when I was here at the conference. Somebody gave me an FPGA with a RISC-V that you can run Zephyr on it and so on. So we're going to start to explore those avenues. But for now, we decided to stay on the microcontroller realm, at least for now. It's not perfect, but it's accessible, I think. From that social perspective, it's better. Yes?
Do you think this might also be expected to do motion control for a motor if you had enough sufficient feedback to it?
Can you say it again?
Do you think this device could also be expanded to do motion control for, say, a motor if you had sufficient feedback?
Yes, actually, because I'm last, I had the possibility of, so let's see this one. So the question is, can we do motion control? So this is one case where we have a DC motor. So we have the power board, and the power board has feedback, and we are actually controlling the speed. So this is speed control. What we're doing here is a little bit too violent because we're just making the motor go one way or another way. So we're making it go both ways. But we could implement position control as well. So both ways. So yeah, we have. It works. That.
So there's enough cycles left in the processor to add extra control loops for that?
If there's no cycle left, what do you mean? Sorry.
Is there enough code space, processor cycles left on here to add more control loops?
I mean, it worked. The way we do it, the way we do our controls, that we have a trigger We are running the control at 20 kilohertz, which is a tenth of the switching frequency. So we have a timer that is precisely ticking at 20 kilohertz. And when it ticks, it preempts everything and it runs the control. So the Zephyr is doing the threading for us, and the timer is keeping it at a very precise, timing cycle. Of course, if your control is too big, maybe those 5 microseconds, no, 50 then, but the time it takes might be an issue. But for so far, we have enough time to handle most, control issues. So the question was if there was not enough time to handle. And for now, we have enough time to handle the controls we've tried to implement so far. Yes?
So you showed that you were using CTS to set up the HR timers and ADC to talk to each other without the micro in between.
Yes.
So that's how it's implemented now. There aren't like structs to initialize.
What?
And then initialize the peripherals. It's all done generic. That configuration is done by generating header files from CTS.
Not really. No. What we did, that's what we wish to do. We want to go that way. What we do right now is that we have got a sample code here. What we have is we have our Zephyr, and in our Zephyr we have our modules. So we have the different modules we had to write, which are shipped with the Zephyr, which makes our Zephyr flavor. And in our ADC driver, we had in the initialization of the ADC driver. So we have this hardware configuration overlay that calls the right function on the ADC driver depending on the kind of initialization you want. And when we initialize, you have to tell the ADC what is its trigger, and you have to tell the HI timer who is its triggering. So we have to do it both ways, both sides, right? And we do that. That's transparent to the user because we had to implement that into our code. And so it's basically, to be totally fair, it's an LL line from ST that we had learned how to use. And we call a function that calls that and that sets it up for us.
Okay, but you're doing that in code. It's not you're not reading those values out.
Not yet.
That's where you want to go.
That's where we wish we could go. We wish that Zephyr could give us the support. Either Zephyr gives us or we work together. It's fine. We can contribute as well. But to get to this point where we can have access to the connection matrix, so then we can set who is connected to who, and then that should be
Software-defined network.
software-defined network, indeed. Software-defined connection matrix. Yes.
I was curious. Is that a software thing or is that a hardware thing? Would you want the hardware connection where it goes directly from an ADC to another ADC side of the system, or on the ADC do like a PWM?
It's a peripheral to peripheral connection. So basically, you're telling one peripheral, your trigger comes from this register, and you're telling the other register, write your trigger. You're telling the other peripheral, write your trigger to this register, and they are looking at the same, and they're triggering at the same time. This is how I understand it. Maybe I'm saying something stupid, but it's peripheral to peripheral. It doesn't go through the MCU. You set it up via hardware, but it is a peripheral to peripheral setup.
You couldn't use I/O for interrupts. So
One of the problems, it's a very good question, why we not use interrupts, is that the time criticity of power electronics obliges you to have a deterministic time code, right? So if we use interrupts, you're no longer fully sure you're deterministic. Sure, you can do some sort of flagging system or collaborative interrupt. You can do some workarounds, but in the end, if you have an OS to do that for you, all you need to do is to be sure that the OS knows it has to stop everything at that moment to run that single task that is the one that needs to be deterministic. So that's how we worked around that issue. Because that's exactly the point. By using Zephyr, we avoid having to build this whole bare metal complex structure of different tasks handling something to each other and so on and so forth. We have one task to handle.
I'm familiar with like a hardware block that's right there and scene where they can connect signals from different cables to another thing. That all happens in a hardware. It's a lot more.
I think it's in the crossbar that it takes place. I mean, again, I'm not totally a software engineer, but I think that takes place. You set up the peripherals between themselves and they run. Sorry.
So that would mean you have to have, the MCU has to support something like
Yes.
that. So it's hardware specific, it's not generic.
Yes.
unfortunately.
It's vendor specific.
Yeah.
I mean, the peripheral to peripheral via the DMA is something that can be enhanced in Zephyr, and that should not be it's like the low-hanging fruit. But the interconnection matrix is a different story. I know what I'm asking for, and I know it's kind of far away and white and floating in the sky, and it's hard to get there. But that's an important thing, an important feature that could be pretty sure useful for everybody, not only for power electronics, I'm sure. Yes.
Are you monitoring the quality of the power output?
If I'm monitoring the quality of the power output, that's one of the things that can be done. We are not monitoring it yet because we have not installed them on the field. To be totally fair, we have not launched the product yet because we are design freezing the hardware. We got to this point where we're comfortable with the Zephyr we have, and we are trying to launch our community. Just maybe I'll get that as a hook. I'll talk just very quickly about what we're trying to do is to create a community that has academia, industry, and makers on it. And our technology is a sandbox. So basically, you have the hardware I showed you, and the intuitive IDE, which is the way we unwrapped Zephyr, and the way we can use it without using it directly. The open data monitoring, because we chose things board so that it can be open source all the way up to the top, and have one single documentation where you can find all the aspects of power electronics, going from the power all the way to the communication. So that's what we're trying to achieve, and also we wish to get to the point where people can either use it as standalone or build racks out of it, and use it for emulating, for fast prototyping and testing stuff. That's where we wish we can get you. So we are not doing power monitoring yet because we have not gotten to the point where somebody in the community has used our power converter to inject power into the grid or something like that. But they could do it because the infrastructure is in place to do that. Yes. Is there any questions online, just in case? No?
So there was a slide where you showed VS Code and platform IO.
Yes. Platform IO is an add-on to VS Code that allows you to flash code to a microcontroller. At least that's how I understand it. It goes beyond that, but it goes way beyond that. But that's one of the main functionalities that I found on it. And Platform IO also, it's a very good way of saying, I wrote this library and I put it in this GitLab. You give it to Platform IO. I say I'm using STM32 or whatever else type of platform to flash. You say that to Platform IO. And then Platform IO is going to magically parse all that information. Download everything you said it should download and compile all that stuff together. So it does a lot of package management for you. And it's amazing. I mean, I don't use West. I don't brag about it. I just got other stuff to do. The day I'm going to need it, my colleague who is back in France, he deployed the USB, the MCU boot, and he had to go through, understand West, and use it, and so on. I let him do it. It's fine. I'm writing the code on the abstraction layers for Zephyr and so on, and I'm very happy using Platform IO because it gives you a button. You push the button, and that's it. VS Code, I never tried to use Platform IO outside of VS Code. Yeah.
Platform IO is just a plugin.
It's a plugin for VS Code.
Okay.
Yeah. Yeah. VS Code is the IDE, and it's cross-platform. I've always been a very Linux fan. I haven't used Windows for over a decade, and somebody else one day showed me in the statistics where over 80% of developers use Windows, and that kind of blew in my face. I was like, okay, so we need to be compatible with Windows, even if we don't use it. And VS Code does that. It gives you the compatibility with Mac OS, Windows, and
Microsoft recently announced we saw a blog where they announced a plugin for that.
all right. A straight plugin for Zephyr, that would be interesting. But still, does it provide the package management? Because
So this is, think of this as a platform where I have a layer on top. You can submit libraries, chunks of code to Platform IO, say it's compatible with this microcontroller. They have targets, I forget their wording, targets, which is the hardware, and then platforms. And Zephyr is a supported platform in Platform IO, so that's
true.
And then so you tag all this stuff, and then it pulls it all for you. So now you don't have to do any code checkout; it does it for you.
No.
So it's literally like clicking like two buttons, and you compile the code, flash it. That's for the
that's exactly what we do. We click in two buttons. I mean, two buttons. We click the button in MATLAB, and then another button here, because here you can do with one if you want.
You don't have to pull any compiler tool, like getting started with Zephyr. I got to download the SDK and the tool chain. You don't do any of that. It just does it for you.
It does it for you.
Yeah, that's the benefit.
That's why, again, it's a matter of ergonomics. A community is as good as the ergonomics you provide them for you. So you have to choose. Do you want a small community with a lot of value per user, or do you want a large community with less value per user? It's kind of horrible to say it this way, but the more you adapt to the greater number of people, statistically speaking, the less these people can bring to your technology, because they are more novice, they're starting as well, and so on. And we want people to be able to do power electronics without thinking about the bare metal, without thinking about the registers, so they can just jump into writing their main, and that's it. Yes?
So you mentioned Martin Creator and Libra Solar
Yes.
and how you're collaborating. It seems like from what I've seen you doing a lot of the same kind of stuff.
Yes. Well,
Are you guys collaborating?
we collaborate a lot, and if he's listening to us, thank you, Martin, for being there, because you're a great guy. We collaborate a lot. Martin does not do such a generic. He's not, he's not as crazy as we are in the sense, so he's not trying to make a power electronic. Yeah, he's not academia, so he's more into the ground. He's got his feet on the ground. His power converters use Zephyr, and they are more function defined. So he does BMS systems and charge controllers, and they are purposeful. Each one of his circuits has a purpose. It's not a generic circuit. So they're cheaper, but they are built with one purpose in mind. We are trying to do a more generic converter, which is obviously different than his, and we use Zephyr a little bit different than he does as well. But ThingSet is his thing. It's something that if you're looking for a way to parse information, it's really good. What he done, it's very agnostic. It's quite fairly good. Hi, we still have 5 minutes, I think. Yeah.
I still have a question.
Yeah. So there's a question from online.
Oh, no, yeah, you have 5 minutes.
Yeah, 5 minutes. Okay. Sure, go ahead.
The last question.
Yeah, not necessarily. We have 5 minutes.
Translate the Arduino to C.
Sorry, say it again.
You mentioned Arduino, that you started with Arduino, like INO files.
No. We didn't start with Arduino INO. Maybe I said something. No, we would like to make the equivalent of Arduino for power electronics, because that's the reference that everybody has, right? So we want to do something that is just as abstract, as easy to use, but not necessarily the .INO. We don't use Arduino's platform at all. Just to be sure on that, yeah. Do we have any last message? That's fine. Thank you. Thank you very much. If you have any questions, if you want to talk more, don't hesitate to come.